Now, as Gerard mentioned before, there is an alternative way to define the same extension without using semantic properties, or without using mathematical definitions like the one proposed by Dung. But you can use what are called labelings, as Bart Verheijfers and then Martin Caminada proposed. And you can have three types of labels: in, out, and undecided. In these slides, the in are green, the red are out, and the gray are undecided. And the conditions are pretty straightforward. An argument is in if and only if all its attackers are out. An argument is out if at least one of its attackers is in, and otherwise is undecided. So in, all the attackers are out. Out, at least one attacker is in. Otherwise is undecided. And once you have these very simple conditions, then you can conclude legal labelings, which are labeling that are covering all the arguments and are giving you, are respecting the three conditions. And these are giving you the complete labelings, which then you can use to derive the other semantics. So given a complete labelings, the maximum undecided is giving you the grounded. So in this case, A, C, E, and G then leaves D and B undecided. This is maximum undecided. This is the ground extension. Maximum in, so if you have a complete labeling that is taking inside as many as in argument, this is giving you the preferred extensions. You just look at the in arguments at this point to derive the extensions. So one is D and the other one is B. As we saw before, B and D are attacking each other. One is defending against the other and vice versa. And if you don't have undecided, that is a stable. And as we saw before, in this simple graph, stable and preferred coincide. But if you look at this graph, there is no undecided. Everything is either in or out. This is a stable extension. The in arguments here is a stable extension. This is a stable labeling. So once again, D and B are alternating. Now, as we can see, the four semantics, although the complete has never been defined as a semantic, but it's just defined as extensions, but are satisfying conflict freeness, admissibility, reinstatement. The grounded is the only one among the four that satisfies strong admissibility. The maximality is satisfied but by all apart from the complete, because it's very possible that a complete is a subset of another complete. We saw that before. This is a complete, but is a subset of the preferred and the other that are also complete. And the directionality is not satisfied by the stable. Now, in argumentation community, people also look inside the computational complexity of addressing problems related to abstract argumentation, in particular very much pulled on. And we know that there are quite important problems associated to Dung's argumentation framework. One of them is to check whether a specific extension exists, whether an argument can be credibly accepted or skeptically accepted, whether a set is an extension or whether an extension is not empty. So an argument is credibly accepted if it is inside at least one extension. So if you have one extension on your graph and your argument that you want to look at is inside that extension, then that argument is credibly accepted. Skeptically accepted, it means that it is in all the extensions. And then you have you check whether a semantics admit an extensions or not, which is the exist. You have a set of arguments you want to verify whether it is an extension of a specific semantics. And finally, you want to check whether a semantics is giving you a non-empty set of arguments. As for the first problem, we know that while complete, grounded, and preferred always exist. So that is trivial, but it's not trivial for the stable. We don't know, we cannot know by default whether a stable exists or not, and this problem is NP complete. Credulously acceptance is polynomial for the grounded. Everything is polynomial for the grounded or trivial. And as Gerhard said before, this is very good for grounded, is giving you very nice computational properties. But for complete, preferred, and stable, proving whether an argument is credulously accepted is NP complete, once again. And we will see later on what a simple way to prove that in later on. Skeptically acceptance is polynomial for complete, and co and p complete for stable, but is at the second level of the polynomial hierarchy for preferred. That's being preferred as some of the most difficult. Semantics. Verification is polynomial for complete and stable, and co and p complete for preferred. And non-existence is basically NP complete almost always, apart from grounded. This is just giving you an idea of how difficult it might be to address some of those problems. As you can see, basically the only nice semantic we have from a computational point of view is grounded. That doesn't mean that we cannot do anything for the others. We will see later on in the presentation, but it's a little more difficult.